Record this, alright? Alright, let's talk about ramps. So you were playing around with ramps yesterday. Now, what you should have seen is that it should have been a sine function, and I'm going to show you why. If you're looking at a ramp, and we are just thinking about, whenever we started with no friction. So the only force that's acting down the ramp is gravity, right? Because there's no friction, nothing acting up the ramp. We're not pushing it, just releasing the object. So if you have a ramp, let's consider this. This downwards force, what would that be? Be gravity, right? Which we know is what? Well, that's the acceleration due to gravity, right? So we'll just call it Fg. Okay, actually, and this would be the angle of the ramp, theta. Now, you learned in grade 11 about something called a normal force. You know what the normal force? And the normal force is a force that acts perpendicular at a surface. So it would look like this. Okay? And it would be perpendicular to that surface. What are you seeing right now? Seeing another triangle here. So here's my force due to gravity. This is my normal force. Now, you see this component here? This over here, that is your force down the ramp. Okay? So this is the force down the ramp. And what is it? Because if you think about what you were doing yesterday, you took a marble, right? You made a ramp, and the marble rolled down the ramp because there's a force acting down the ramp. We know it's gravity, but it's what component of gravity? So this angle over here is the same as this one. These two are the same. This one and this one is the same. So then what would this component be? This is your hypotenuse, right? This is my right angle over here. This is my hypotenuse. So how do we figure out what this force down the ramp is? Well, it's the opposite side. So it would be what? It's sine theta times the hypotenuse, which is my weight, or my force due to gravity. Okay? That's why you should see a sine function when you graph your results of angle versus acceleration. Because if you look, you'll see your weight is your hypotenuse. Here's your theta. The opposite side is the force down the ramp. So it's a function of sine theta times the weight. Now the normal force, what would it be a function of? It's not sine theta, it's the adjacent side. So it will be cosine theta. Alright? This is important because we're going to talk about friction later. And if you remember from grade 11, friction is what? Mu times Fn. But in this, so for a ramp, what would it be? It would be mu times cosine theta times Fg, because what's Fn? Fn is cosine theta times Fg, right? I'm going to look at some questions for ramps. We're going to first talk about no friction, and then we'll talk about friction. Alright, so the first two, I believe, have no friction, and then we're going to talk about adding friction to it. Okay? So let's look at the first question. How long would it take a marble to roll down a ramp with no friction if the ramp were 10 meters long and the incline was 90 degrees? Alright? What? I was just testing you, see if you're paying attention. Now, alright, so the ramp is 30, so here, what do we know about the force down the ramp? We said that the force down the ramp is a function of the weight. I really should be writing the weight first, times sine theta. Okay. Now, we know that force is equal to mass times acceleration. So the force down the ramp is the same as the mass of the marble times the acceleration down the ramp would be equal to the mass of the marble times the weight of the marble, times the g value, which is 9.8, times sine theta. You'll notice I didn't give you the mass of the marble because guess what? It's not important. Okay? So the acceleration of the marble down the ramp is just a function of g sine theta. And that makes sense because we know that everything falls at what? The same rate. So the acceleration down the ramp is just g sine theta. So that would be 9.8. Sine 30 is what? 0.5. Okay. So that means the acceleration down the ramp is 4.9. So far, so good. Change the color. So this is what we know now. All right. We have the acceleration. We have it's 4.9. The distance. Distance is 10 meters. Acceleration is 4.9. Initial velocity would be what? What do you think? What should we assume the initial velocity is? Yeah, I'm going to assume it's 0, right? Although we can't answer the question. So we're going to look for time. Alexa, what equation do we use when we have an initial speed? So if we look at the equation with no initial velocity, we could use this one. All right, we could rearrange for t. So t would be 2d over a. Okay. So that would be the square root of 2 times 10 over 4.9. All right. So that's 20 over 5 is 4. So that's about 2 seconds. Okay. About 2 seconds. Not exactly, but I'm just going to round it off because I don't want to waste time pulling that calculator out. Okay, so force down the ramp is a function of the weight times sine theta. Okay? All right, can I move on to the next one? Since I'm recording this anyway, so we can come back to it. Hey, this is a good way if I can record it, get through things a lot faster. All right. Look at this question. We have a car going up a ramp. So we're going to do a 30-degree ramp again. So 30 degrees. So we have a car going up a ramp. Got my car. All right, here it is going up a ramp. Let me pause this because we have a visitor. And that pause is brought to you by McCain's Pizza. Okay. Oops. Let me get rid of this. Okay. So that's an ugly part. We have a car accelerating up a ramp at 2 meters per second squared. All right. Now, let me ask you a question. Do you guys remember net force calculation? So remember, net force is what? The sum of the forces. So in this case, I want you to think about the ramp, okay? There's a force acting up the ramp, and then there's a force acting down the ramp. We're not going to worry about friction here, so we don't need to worry about the normal force, okay? Because there's no friction. So, because there is a force going down into the ramp, because we know there's the weight of the car, and we know there's a normal force, but we're not going to worry about that because there's no friction here, okay? So, I want you to think about this. This is the force down the ramp over here. This is the force of the, we'll call it the applied force, because that's the engine, right? The net force then would be what? It would have to be the sum of, what two things? Right, it would have to be the applied force plus the force down the ramp, but that's going the opposite way, so we can make that negative. So it will look like this, right? The net force would be the applied force minus the force down the ramp. The fact that the car is accelerating 2 meters per second squared up, well, what force do you think that would be? You sure? It's accelerating up the ramp at 2 meters per second squared. That would have to be the net force. This has to be the net force. So the net force would be the mass times the net acceleration, which would be 1,000 times 2. So the net force is 2,000 newtons. So we can write our equation as this. We can say, okay, look, the applied force is actually going to be the net force plus the force down the ramp. The applied force is going to be the net force, which is 2,000 newtons, plus the force down the ramp. Now, what's the force down the ramp again? We defined it as what? FDR is the weight times sine what? Theta. The weight being mg sine theta. So the force down the ramp would be the weight of the car, which is 1,000 times 9.8 times sine 30. That would be 9,800, and half of that would be 4,900. So I'll put it over here. So our applied force then would be 2,000 plus 4,900, which is 6,900 newtons. And that makes sense because, look, your net force is going to be less than your applied force because you have the engine pushing up the ramp and you have gravity pulling down the ramp. So your net force is 2,000. So your applied force must be bigger. It has to be bigger than the force down the ramp. Otherwise, what would happen? It wouldn't be going up, right? If the applied force is less than the force down the ramp, it would actually be moving down the ramp. Let's pause again for our second break. Okay. All right. Next question. Next ramp question. How are we doing? Oh, it's already 12:24? Holy moly. All right. It's already 12:24? Oh, wait. This is the curriculum support. We're done at... Okay. All right. How long... I thought it was regular schedule. How long would it take a wooden block... Now we're going to introduce friction, okay? How long would it take a wooden block to slide down a 10 meter ramp? We have the coefficient of friction. It's 0.1. Remember what the symbol for coefficient is? It's this funny thing. Mu. Remember that? And mu is defined as FF over Fn. So FF is mu Fn. If you don't remember it, hopefully this will make sense. Okay. So our ramp is 20 degrees. So we have a wooden block on the ramp. So here's a wooden block. We know it has a normal force. We know there's the force down the ramp. There's nothing pushing up the ramp. So, but there is something that is actually not pushing it, but is actually resisting the object as it slides down. And that would be friction. Okay? So here are your forces. And obviously there would be the weights, right? Which is Fg. So these are your four forces. Okay. So, it would stand to reason if we could figure out the net force, we can solve this. So what do you think the net force would be in this case? It would be the sum of what two things? Yeah. Friction minus force down the ramp, right? Because friction is preventing the object from sliding down the ramp, and the force down the ramp is trying to make the object slide down the ramp. Okay, so what's our friction? Well, it's mu Fn, but what is Fn? Do you remember what Fn was? Yeah, but remember how we defined it though? We defined it as what? If you recall, we defined it actually as, yeah, so it's the weight times cosine theta. Okay, so the normal force is basically the weight times cosine theta. So let's put these together. Force of friction is mu times Fn, right? So Ff is mu. What's mu? Mu is 0.1 times Fn, and Fn is Fg cosine theta, right? So Fg cosine theta okay. And we're going to subtract that from what? What's the force down the ramp? How do we define that one? Fg what? Times sine theta, right? Okay. So the net force is what? Now you're like, okay, I didn't give you the mass of the block. Do you think we're going to need it though? What do you think? Think we need it? We'll find out. Let's see if we need it in the end, okay? So, 0.1 times Fg. Fg is m times g, right? So we're going to have, actually let me give myself a bit more room here. Let's slide this over here. Okay, so let's do this. So the net force is equal to 0.1 times Fg. Now we don't know what the mass is, but we do know what g is, right? We know it's 9.8 times cosine 20. Okay, that's the first part of my equation. Minus mg, we know it's 9.8 times sine 20. Okay, so let's make this a little bit easier. So 0.1 times 9.8 times cosine 20. What is that? What's 0.1 times 9.8? Well, 0.1 times 9.8 is 0.98. What's 0.98 times cosine 20? What's that? What is it? So this is 0.92 times m, because we don't know what m is. Minus, what's 9.8 times sine 20? Sorry? 3.35 times m. All right. What's the definition of force? M times A. So it would stand to reason the net force is the same as the mass times the net acceleration. And if you look, what do you notice? We don't need the mass, do we? So what's the net acceleration? Is just 0.92 minus 3.35. Okay? What's that? 2 point. Okay. Now we have the acceleration down the ramp. Okay? So we have the acceleration down the ramp. We're told the ramp is 10 meters and the initial velocity is 0. So we can do what we did before. We can figure how long it takes to go down the ramp. We could use the equation which we looked at before, which is this one, right? This is the drop equation rearranged. So we have the distance. We're told the ramp is 10 meters. We're told the acceleration down the ramp is negative 2.43. The distance is down the ramp, so this distance should be actually negative. So the negatives are going to cancel out. Or you can just use your, use your common sense. Say, the negative sign just indicates down the ramp, so we don't need to worry about that in the, with the fact that it's being square rooted here. So, what does that give you? Just 20 over 2 point. It's about like the square root of 8. What is it? Should be less than 3. 2.87? Okay. So 2.87 seconds. Alright? Okay. So we're getting flashbacks of net force now and friction. So now we're just adding, because now we're talking about ramps, right? A lot of the stuff is what you learned about in grade 11. You may not have done ramps, but it's very similar. Okay, one last question. Now, again, this type of question looks like you don't have a lot of information, but you don't need a lot for this one. We have a ramp, and we have a textbook on it. Now, if the ramp is not elevated, the textbook doesn't slide. But as we start to elevate the ramp, the textbook at some point will slide. So there's going to be a point where if there's a book on a ramp, it will start to slide because the force down the ramp will have exceeded the force of friction. But there's a maximum angle where if they're equal, if the force of friction is equal to the force down the ramp, then there's no movement. The reason why there's no movement is because of Newton's first law. Remember Newton's first law, Law of Inertia? If the textbook is at rest, the textbook's at rest, and the net force is 0, then the textbook stays at rest, because an object's going to want to do what it's initially doing, right? So, if the textbook isn't moving, and the force of friction is equal to the force down the ramp, and they're equal, the net force is 0, textbook stays in place. But as soon as you, increase the angle even slightly to the point where FDR is bigger, then what happens? Then it starts to slide. Okay? Alright, so, this is what we know. Net force would have to be this. Correct? And if the net force is 0, then what happens? Nothing. Correct? The net force is 0, nothing happens. Okay? So then we could say this. We could say FF would have to equal force down the ramp. Now, how do we define FF again? It was what? FF is the same as mu Fn. And FDR was the same as mg sine what? Theta. But we said that Fn is actually what? Fn is actually, right, it's actually mg cosine theta. So if we plug that in here, we get this. Oops, sorry. The mu mg cosine theta is equal to mg sine theta, right? Because Fn is mg cosine theta. What do you notice? Mg cancels out. So then mu is actually just a function of sine theta, because we can cancel the cosine theta and move it over here. It's just a function of sine theta over cosine theta. And what's sine theta over cosine theta? Aha. Tan theta. So guess what? What's mu? Mu is 0.1. So we can solve for, theta. We just do the inverse of 0.1. So in other words, if you want to know the minimum angle or the maximum angle, all you have to know is the coefficient of friction. And if you take the inverse tan of that, that gives you your angle. So what would be the inverse tan of 0.1? What will theta be? 5.7? So it'll be 5.7 degrees. Which means we could elevate this ramp to 5.7 degrees and it won't slide. Anything more than 5.7, then FDR is greater than FF. What happens? That's a slide. Okay? The end.